let's continue our discussion. Now we are going to discuss about the concept of potential energy. So what do we mean by potential energy? So this is a kind of energy which is possessed by a body by virtue of its position, or maybe a system by virtue of its position or configuration. So you can say energy possessed by a body or a system due to its position or maybe its configuration. Okay, let's take an example. So you can say gravitational potential energy. So you can say that if a body is being raised up to certain height, let's say this height h, this body will move downward. Let's say this is Earth's surface. So this body will move downward if it is released from here. So a body raised up to certain height has energy by virtue of its position. And this energy, we can say this energy is an example of potential energy. In the same way, you can think of spring potential energy also, like stressed or compressed spring. So if there is a spring here and there is a mass attached to this spring, and you have displaced this mass from its equilibrium, means its relaxed position, neither stressed nor compressed. Then if you have stretched it up to certain displacement, let's say x, and you release it from here, it will start its motion towards this equilibrium or the neutral point. So after stretching this spring or maybe compressing this spring, this body will start its motion when you release the external force which is elongating or compressing this spring. So you can say it has potential energy. In the same way, you can say for a stressed rubber band, it has potential energy. So let's discuss more about this gravitational potential energy. So a little more about gravitational potential energy. And at the end, we are going to generalize it. So gravitational potential energy is the potential energy possessed by a body when it is being moved in a gravitational field. You can say moved against gravitational force. Let's go to next slide and then we can discuss more about it. So let's say this is Earth surface and this is Earth surface, and let's say a body of mass m has been raised to certain height h, and here we are going to restrict ourselves in a way that this h is much smaller than this re, which is radius of the earth, so that we can think of that gravitational force on this body, this m, we can think that it is uniform, it is not changing too much, because this is center of the earth, and if we move away from this center, the gravitational force will be varying with this relation. So we have to restrict ourselves for timing, because we are going to discuss these things in detail when we are going to discuss gravitation topic. So for timing, let's say that h is much smaller than radius of the earth. So in this case, we can think that this acceleration due to gravity is constant, or you can think that gravitational force on this body is constant if its mass is constant, and we are discussing for a constant mass body. Okay, now let's discuss about its potential energy. So if a body is being raised, let's say here on the earth surface, here, let's say it has no potential energy here. Let's say v of h is 0. We are taking reference this earth surface where we are taking that potential energy is 0. Although we can take anywhere to be potential energy zero, but we have to stick to that statement for entire discussion. So based on our convenience, we can take anywhere the reference point, and anywhere we can take that potential energy is zero. This thing we are going to discuss in more detail. For timing, let's take that Earth surface is our reference point, and here potential energy is zero. So if you are raising this body up to height h, it will have now potential energy of, let's say, V of h is now m into g into h. This much potential energy is going to rise in this body, and this potential energy is under the influence of this is because of the gravitational force, so we can call it gravitational potential energy. Now what is happening exactly here? What we have done, we have moved a body against a restoring force. So let's say this gravitational pull, which is mg, is acting to pull this body towards the center of the earth, and this body is going to reach up to here only, let's say up to the surface. So what we have done, if we have raised this body up to height h, we have done a work against this force, this restoring kind of force. So what we have done work, and this work is mg, which is force. Look, if we want to move this body up to height h without accelerating it, at least we should apply this much force, that is mg, to balance it. So let's say we are moving this body up to height h without accelerating it, and then we have to apply a force upward direction, which should be equal to this gravitational force in its magnitude and just opposite in its direction. So let's say we are taking the upward direction here to be positive, and any vector towards downward direction we will take negative. So here Fg is, you can say, minus mg, and this Fa, you can say it is positive. So you can write Fa is mg and into h. This much work we have done against this force, and this work is going to reflect in its change in potential energy. So the potential energy is being raised by mgh, and if we are taking this to be reference, so at this position the final potential energy will be this much mgh. Okay, so what we have done here, we are some external force working against this restoring force, and that work done is being reflected in terms of its potential energy. In other words, we can say that negative of this work done means work done by this restoring force, gravitational force, and if we are taking negative of that work done, that will be the potential energy raised in this body. So you can say negative of, it will be the same. Just take a look here. Negative of work done by this force to pull this body from here to here. So this will be minus FGH, and FG is already minus mg. So we will have here minus minus plus, and then it will be mgh, which is the same as we have seen here. So what we can say here, in case of any restoring force which is trying to bring back the body to its neutral or equilibrium position, if we have acted on the body against this restoring force, the amount of work we have done against this force, let's say here Fg, that amount of work will be the rise in the potential energy of the body. So, or you can say of the system. In other words, we can write one more thing, that force let's say here gravitational force, we can write gravitational force is negative of gradient of potential energy. Okay, you can see it. This will be minus d, and this is mgh, and this is h, and you know m and g are constants here, so this will be minus mg outside, and then we will have dh by dh. This is 1, so you will have fg equals to minus mg, which is the force. Look, here we have considered this force. Okay, let me make it more clear to you here. So this is gravitational force. We have taken our convention. Upward we will take positive, downward we will take negatives. For the vectors which are directed upward, we will take positive signs for them. So what is happening here? We have one more thing here, that for obtaining this restoring force, we can take the negative gradient of potential energy, and then we will arrive at the same scenario, that is F equals to minus mg, and here minus mg is the force against which some external agency has been worked, and that resulted into the rise in potential energy. Now let's move to the next point. Suppose we have left this body from height h to come back to the earth surface. So it starts here, let's say initial velocity 0, and then it hits the ground with some final velocity, and we know v square minus u square equals to 2gh here. So v square equals to u is 0, 2 and g and h. Now 1 by 2 v square equals to g h, and if we are multiplying both sides with mass of this body, here we will have mv square, half mv square equals to mgh, and you can see this is potential energy of this body here. So you can write potential energy, and you can identify this term here. This is nothing but kinetic energy of this body at the moment when it is hitting the ground. So what is happening at this point here? We have taken reference. So potential energy is 0, but there is kinetic energy, half mv square. And at this point here, potential energy is something that is mgh, and we are releasing it from here. Ultimately, what is happening? This potential energy is being manifested into kinetic energy. Look, as this body starts its journey from here towards the surface, let's say surface, ultimately it is going to the center, but let's say surface here. So this potential energy, when this body is released from this situation, this potential energy is being manifested into kinetic energy here. This is one result, you can say. Okay, let's go back to the previous slide to get some interesting results. What is happening here? Force equals to negative of gradient of potential energy. Okay, this what we have just verified here, that this mgh, if it is potential energy, so negative of gradient of this mgh will be the force under which potential energy is being changed, means against which some external factor is working and potential energy of the body or a system is being changed. So let's carry this thing on the next slide, and then we will derive a very beautiful result. So Fg equals to minus dVh by dH. So you can write here minus Fg dH equals to dV, or you can write Fgh equals to minus dVh. Now you can integrate it from h initial height to final height. And here you can integrate it, initial potential energy to final potential energy, let's say. So this Fg we are taking nearly constant because we have restricted ourselves to this uh, approximation that h is much smaller than the radius of the earth here. So here Fg, gravitational force, and this one, let's say initial height is 0 and this final height is, let's say, h. So you can write here h minus 0 equals to here minus final potential energy minus initial potential energy. So what is happening here? Let's move to the next slide. Fg into h equals to minus final potential energy minus initial potential energy. Okay. So what is happening here? We can see that work done by this force here, the gravitational force. So work done by this force is depending on the final position, because this potential will depend on position only. So the final position and initial position, but not the way or the path through which this body has been moved. So what does it mean? Let's say this is Earth surface. Let's say V initial here is 0, and you have moved this body of mass m up to height h. So it has potential energy here, final mgs. Now with the same mass, there is another body, and this body is being moved this way from here to here, then up to height h, and then back to here. So this has been moved along this path. Again, this body will have final potential energy of mgs if it has been moved to height h. So no matter which path has been chosen, path 1 or path 2, the change in potential energy will be the same as long as this h will be same. So the work done by this force is independent of the path chosen. So you can say this kind of force are examples of conservative force. So this is a type of conservative force, and conservative force is nothing but the force work done by the force depends on the initial and the final position of the body, but not the path. So this kind of forces are called conservative forces, and gravitational force is also an example of conservative force. You can think of another example like electrostatic force. Electrostatic force is also an example of conservative force. So in the influence of electrostatic force, if you have moved any charge from point A to point B, so the change in electrostatic potential will depend only on the positions, but not the path you have chosen. Means the negative of work done by the electrostatic force will depend on the positions, initial position and final position of the charged particle, so or charged body. So electrostatic force is also a kind of conservative force. And here we are discussing about gravitational force only. So let's take one more example and then we'll discuss about the conservation of mechanical energy. So let's say that a body is being released from here, from height h to the earth surface, okay, and vertically downward direction, and another body which has been released on a slope, but from the same height. And now, what will be the speed of this body in the two cases just before hitting the ground? So you can think by yourself and you can reply what it should be. Let's say final velocity or final speed here is v, and in this case the speed is, let's say this one is v1 and this one is v2, let's say, and then you have to calculate the final speed here. So let's say the body has mass m. You can try by yourself, and for your reference I can say v1 and v2 should be the same, because the potential energy here is mgh and here potential energy is mgh, and then this potential energy, in both the cases these potential energies are being manifested into kinetic energies to these positions. So you can continue by yourself and you will arrive at this in v1 equals to v2. Now, the conservation of mechanical energy. Uh, Look, this will be happening only when we are talking about conservative forces. Means the body is moving in the influence of conservative forces. So non-conservative forces like friction, where energy loss is happening in other form, like heat or sound or light maybe. So there this thing is not going to be uh, valid. But here, when we are talking about the motion under the influence of conservative forces, then this result will be valid. So what is this result? We call it conservation of, this is our conservation of mechanical energy. Okay. So what is happening? The total mechanical energy, that is kinetic energy plus potential energy. Total mechanical energy is here, kinetic energy plus potential energy. So the total mechanical energy remains conserved. That is, if a body is moving under the influence of conservative force, so its initial mechanical energy will be equal to the final mechanical energy. And we have seen this thing already here. Let's say there is a body releasing, we are releasing it from height h, and then here it has potential energy mgh, and it starts here. So kinetic energy will be 0. And when it is about to hit this ground, and we have chosen this ground to be reference, so potential energy will be 0 here, but the kinetic energy, that is 1 by 2 mv square, will be m into g into h. You can do it by yourself, or you can go back to previous slides. So what is happening? Let's say this position is position A, this position is position B. So mechanical energy at position A is equal to mechanical energy at position B. So this body is moving under the influence of gravitational force. This body is in gravitational force field, that is conservative in nature, and the mechanical energy, total mechanical energy, remains conserved. The only thing is here, at position A it has potential energy and no kinetic energy, and at point B it has kinetic energy and potential energy is 0. But altogether, potential energy plus kinetic energy at both the points, it has mgh. Let's take an intermediate point anywhere here and check whether kinetic energy plus potential energy, we are getting total mechanical energy mgh or not. So let's say this position here is, let's say this is z above the earth surface. So potential energy will be mg into z here at this point. But this body has been moved by this distance s minus z. So it has velocity here. Let's say v1, you can write here v1 square equals to 2g and this distance, that is h minus z. And now kinetic energy at this point will be 1 by 2 m v1 square, that will be 1 by 2 m, and here we are going to multiply 1 by 2 into m, this one was, and this is kinetic energy at this point. So potential energy, let's say this point is point C. So potential energy at point C is mg, this one z, and kinetic energy at point C is 1 by 2 m v1 square, which is equal to mg s minus z. And you can see if you are adding these two things, that is mgz plus mgh minus mgz, here you are going to get this thing. So it will be mgs. So again, at point C, mechanical energy is nothing but mgs. You can, this is an arbitrary point in between these two points. So you can say that anywhere during its journey, the total mechanical energy is mgh only. Okay, in the next video, we are going to take one example, about this conservation of mechanical energy. We will solve an example from NCERT textbook, and then we will move to the next point, potential energy of a spring, and we will do a detailed discussion about that. So that's all for this video.